So next up, we have Paul Lucey talking about shy volatiles, how volatiles in the lunar polar cold traps may use physics to escape detection.
Okay, Elizabeth, do you hear me?
Yes, I do.
Okay, so let's see if I know how to advance my own slide. Okay, well, let's cut to the first slide here. So the basis of sort of everything I'm going to be saying for the next few minutes is centered around the fact that the stability of volatiles in the cold traps is exponentially dependent on temperature. So what you're seeing here on the left is from the classic Zhang and Page paper showing the sublimation rate of volatiles in units of meters per billion years versus temperature. You can see those curves are extremely steep. So the upshot of this is that there's a very narrow range of transition from where a volatile acts like a volatile, it's chiefly in the vapor phase, or the volatile acts sort of like a rock. On the right is just a recast of what the Zhang and Page plot is. This is for water ice, and it shows the lifetime of 100 micron grain versus temperature. And you can see that in this range from about 100 to 110 K, the 100 micron grain can last the age of the solar system on the left to just a few 100,000 years or even much less on the right. So what I'm going to be showing you are temperature variations within the cold traps that span this critical range and can affect the detectability of volatiles by sensors that are coming up in the next few years. So let's see. Inability to advance slide. Okay, so the key parameter that have been used to map stability is our data from the Diviner radiometer. There's a lot of exposition here, but the short story is that Diviner provides temperature measurements in the cold traps at about 200 meter resolution. But within a Diviner pixel, the temperature lunar surface can vary substantially at all the scales about a centimeter. And the variation in the PSRs within those pixels is no different. So the temperatures that are used to produce the stability maps don't reflect precisely the actual temperatures that are experienced by the volatiles within those particular pixels. And the problem is really acute in PSRs that are undergoing indirect lighting, and when it's at its maximum, I mean, it's optimum for imaging. And I'll show that this may give rise to false negatives and will definitely dominate the uncertainty associated with what the volatile abundances are that we derive from the cold traps from these measurements. So how does subpixel temperature variation arrive? So the lunar surface is rough, and on the illuminated surface, this rough surface presents a range of incidence angles to the sun. This is a plot from J.P. Williams et al. The lunar surface is highly insulating, so the sun-facing slopes can achieve fairly high temperatures, whereas the slopes that are facing away from the sun maintain low temperatures, and shadows make this problem even worse. So what about the PSRs? So a PSR has a similar situation. Here's a picture of Shackleton, that illuminated wall that falls into the interior of Shackleton. The light falls on the sun-facing slopes of the roughness within the crater, not the sun-facing slopes, but the crater rim, illuminated crater rim facing slopes. And that gives rise to a wide range of temperatures within a Diviner pixel that complicates predicting the stability. So what we've done is create a model. So this is an image of a computed fractal surface. We did two varieties of roughness, 6 and 23 degrees. So 20 degrees is the solution to diviner measurements of off nadir, which are dominated by this low, short range roughness. 6 degrees roughness occurs at somewhat larger scales. So we looked at these two cases. We illuminated the surface with a reasonable range of azimuth and elevations, so 90 degrees of azimuth and 1 degree range of elevation, computed the temperature from radiant of equilibrium, computed the diviner apparent temperature, what diviner would perceive, and then compared these to sublimation lifetimes. So we looked at two cases, quote, Shackleton-like crater, where the rim is about 20 degrees off the surface, and a Shoemaker-like crater, a large flat-floored crater, where the illumination is about 5 degrees off the surface. And here's a nadir view of Shackleton. So we looked at 90 degrees of azimuth and varied this azimuth to modulate the amount of lighting that the surface would get. So here's some results. So the little inset pictures is what the surface looks like in units of temperature for these cases. So this is the 20 degree elevation version, think of like Shackleton. The RMS roughness of 6 gives a very narrow range of temperatures around the apparent temperature. So this is the best case. But if we look at this, the RMS roughness of 23 degrees, there's a wide range of temperatures that go all the way down to a background, which in our model is dominated by heat flow. So this surface is starting to complicate the stability of volatiles in the surface. So with the 5 degree elevation angle, this is the Shoemaker case, and also diviner temperature of 100 K. The RMS 6 it shows a wide range of temperatures, bimodal distribution. And then the RMS 23, which again matches the diviner measurements on the illuminated surface, is strongly bimodal with a combination of relatively high temperatures and low temperatures present within the same pixel. So the problem starts to arrive is that while, I'll back up for a second, while this on the right, you can see a bimodal distribution. So let's call it a roughly 50-50 distribution of temperatures that are relatively high, near about 130, 140 degrees, and low, they have about the same area. The amount of signal you get from 3 microns, where you want to actually measure, let's say, water abundances, is weighted by the amount of signal that's available. So the cold parts, thank you. The cold portions are biased towards low signal. So I'm just going to show this real quick. These are the different cases, but this is a cumulative plot. So that as you go from the 50 degree temperatures up to about 90, there's very little signal from those so-called icy surfaces. The signal is dominated by the surfaces that are illuminated and are warm and nominally dry. So this is a complicated plot, but the short story here is that most of the signal, in all cases, more than 75% of the signal, and sometimes more than 90% of the signal, is from the surfaces that are way too hot to preserve volatiles. This is the nadir case. Off nadir viewing can either improve or exacerbate this problem. So the conclusions and implications, that the spectral measurements can underestimate the surface ice abundances. These are passive measurements, like were done by M-Cube and will be done by Trailblazer. I didn't go into it, but small amounts of surface ice can be present even where maximum diviner temperatures are above 100 K. Off nadir measurements can increase the apparent area of cold surfaces friendly to ice at the expense of total signal, but that total signal is mostly dry. And the abundance uncertainties that we are actually going to derive for ice are strongly tied to the estimate of the roughness. And I should point out that the laser reflectance measurements by lunar flashlight are immune to the bias from this issue and are uniquely suited to measure the effect of this off nadir. Thank you.
Awesome. Thank you so much. That was really interesting.